Hello and welcome to our second and final lesson in our halogen derivatives unit, focusing on the halogenoalkanes. Today's lesson, entitled Nucleophilic Substitution Reactions. We're going to understand the mechanism of SN1 and SN2 nucleophilic substitution reactions of halogenoalkanes and describe the relative strength of the carbon-halogen bond. So we introduced a number of these nucleophilic substitution reactions in the previous lesson. Nucleophiles including hydroxides, including cyanides, and including ammonia. We're really going to look at the mechanisms and how they occur stepwise today, introducing two new terms, SN1 and SN2 type reactions. So let's just recap. In halogenoalkanes, a substitution reaction where a nucleophile will attack the electrophilic delta positive carbon atom in the carbon-halogen bond. That's what the nucleophilic substitution reaction is. We end up with a product where the halogen is left as a leaving group and the nucleophile has substituted itself into its place. Two variants that we can have, SN1 and SN2 type reactions. So you might be able to guess the S and the N. S stands for substitution, nucleophilic is what the N stands for. The number refers to the number of species that occur in the rate determining step. Very important, it does not refer to the number of steps in the mechanism. As we'll see, an SN2 mechanism occurs in one step, whereas the SN1 mechanism occurs in two steps. Now, it's a very easy mistake to make, to think the number refers to the number of steps, but it's not. It's referring to how many species are involved in the slowest step of the reaction. Now, this is going to make a lot more sense as you continue on with your chemistry education and look at a bit more advanced reaction kinetics. But just for now, it's something we've got to be able to remember and make sure that we do not get it mixed up. So the mechanism the reaction undergoes depends on, among other things, the relative stability of the carbocation. Okay, let's summarize them and then we'll look at both in depth. So like I say, SN1 is our two-step process. It first involves the leaving of the halogen. So an intermediate carbocation is initially formed, the leaving group bond is broken. So the halogen leaves the halogenoalkane, heterolytic fission, it takes that electron pair with it, leaving an electron deficient carbocation intermediate. Then we have the second step where we have the nucleophilic attack from our nucleophile, whatever it is, it forms a new bond with this carbocation. Now, we can consider why it's called SN1 because we have a slow step and we have a fast step. Breaking the initial bond is a slow step, but once the carbocation is formed, we have a very good electrophile and then we have a nucleophile that can very quickly form the new bond, so that's the fast step. So that's why it's called an SN1 mechanism. Only one species is involved in the rate determining step. So our slowest step of the reaction is called the rate determining step, the step that determines the rate of the reaction. Now we have only one species, which is the halogenoalkane, because that's the only species involved in the slow step, which is the breaking of that carbon-halogen bond. Because the next step, as soon as that happens, the next step occurs very, very quickly. Let's compare that to our SN2 reaction, where we have SN2 as a one-step process. So in this instance, the nucleol forms the new bond simultaneously as the leaving group bond is broken. So in this case, the bond is broken first and then the bond is formed. These occur synchronously. They occur at the same time. The bond breaks as the new bond is formed. So only one step is involved in the mechanism. So therefore, we got two species. Both the reactants are involved in the rate determining step. The rate determining step in this case, there is only one step. So that is the rate determining step. So that's where the two comes from, the SN2 reaction compared with the SN1 reaction. Let's look at them in a bit more detail here. Let's look at the mechanisms. Let's see where the electrons are going, where they're coming from, what bonds are breaking, what bonds are forming. Like I say, our SN2 happens in one step. The new bond is formed and the old bond is broken synchronously at the same time. Rate is dependent on two species. Only one step, we have a rate determining step that involves both the reactants too. Now this occurs in primary halogenoalkanes. This is because in a primary halogenoalkane, if we were to initially break the bond, I'll draw an example of this. Let's say if I've got something like chloromethane, let's just keep it nice and simple. This, well, let's say chloroethane. let's do that molecule there. Now, if I were to break this bond and form the carbocation intermediate, what I would end up with is a primary carbocation. We've only got one alkyl group donating electron density into that bond. And we've looked a few times now at the different stabilities of our carbocations, where our primary carbocations are the least stable. Well, at least there's the methyl carbocation that is less stable than that. But when compared to the secondary and the tertiary, our primary ones are the least stable. So that means that if we did it via a two-step reaction, we would make a very unstable intermediate, and the reaction wouldn't want to do that. So what happens instead, because we have a very poorly stable carbocation, it will occur in just the one step. There's also this effect of something called steric hindrance. Sterics refers to how congested the central atom is. So we have a lot of steric hindrance if we have big bulky groups around the carbon that's the electrophile. We have low steric hindrance if we have just a small amount of sterics. So if we look here, we have, a reasonably bulky methyl group, but then we have two very small hydrogen atoms. So we don't have very much steric hindrance around the atom that we are doing the reaction with. So the steric hindrance is the prevention of intramolecular interactions due to the spatial arrangement and congestion around an atom. Primary halogenoalkanes have relatively little steric hindrance, so the nucleophile is able to form a new bond with a delta positive carbon without too much interference from the other groups bonded to it. So this combination of issues, or not issues, but this combination of factors would be a better word. The fact that we would make a very unstable carbocation, contributed with the fact that there's not very much congestion around the central carbon in a primary halogenoalkane, means that we would most likely favor the SN2 type reaction that occurs in one step. Let's have a look what this looks like. The general mechanism looks like this. So we have some species where X is our halogen and we've got our R groups. Now in this case, they would be one alkyl group and then the other R groups would just be hydrogen, just small hydrogen atoms. We get nucleophilic attack from the lone pair of electrons on the nucleophile to that central electrophilic carbon atom. Now again, little steric hindrance, we've just got small hydrogens around it, so this can form the bond as the bond breaks, and we end up with this intermediate that has three bonds, one bond that's been formed and one bond that is being broken. So this would give us 5 regions of electron density. If we think back to our VSEPR theory, valence shell electron pair repulsion theory, we would have a trigonal bipyramidal geometry here before we get the complete severing of our old bond and the complete forming of our new bond. So our intermediate and then the halogen leaves and we have substituted it with our nucleophile. Give this a go. So I've given you a general mechanism. Can you use this general mechanism to show what the mechanism for the reaction between 1-bromopropane and hydroxide would be? And then can you justify why the reaction would occur via an SN2 mechanism? Give that a go and then we'll check it on the board here. So 1-bromopropane and hydroxide. So I'll draw my bromopropane. Bromo on carbon 1, H. Put the H's in. Now, when we're drawing our mechanisms, we've got to make sure that we have our partial charges. We've got to make sure that we have the lone pair of electrons on our nucleophiles, because nucleophiles need to have a lone pair of electrons. So we can see we've got one alkyl group, so we are primary halogenoalkane. We've got 2 very small hydrogen atoms bonded, so that allows the steric hindrance to be minimal enough that we can come in and we can form the new bond as the bromine breaks. And then we form our intermediate where we have the, let's keep that at bromine, where we have the bromine bond breaking. We have the new hydroxyl bond being formed. And then we have 2 hydrogens and then the rest of our carbon chain that I'll just summarize as C2H5. So this is an intermediate, negative charge on that intermediate, and then eventually the bromine bond breaks, completely severs, the hydroxide bond forms, and we end up with the substitution reaction from the bromopropane, 1-bromopropane to 1-propanol or propan-1-al. And that would be the reaction. I'll do a little arrow there to make sure that we have all the information that we need. So one-step reaction, because the carbocation would be very unstable. If we formed a primary carbocation, we have low amounts of steric hindrance. That means it can occur in one step, so an SN2 mechanism. Now we can illustrate this on reaction enthalpy profile diagrams. If we consider the 3 steps to our reaction, we're going to have our reactants here, which is our halogenoalkane and our nucleophile. We're going to have a high energy transition state, which is that one there, and then we form our products once the reaction is complete. Let me draw that for us and show our bromopropane example what would be formed at each step. So we start off with our reactants, high energy transition state, and then we form our products. So at this point here, how am I going for space? This point here, we would have the bromopropane. Maybe I'll do some skeletal diagrams. So the 1-bromopropane like that, and our reactant, which is the hydroxide. Then, as the nucleophile comes in and begins to form this bond with the delta positive carbon, and that bond starts to sever, we're going to have much higher energy because we have a lot of electron density around that carbon. We're going to have lots of repulsion. We form that transition state which has more bonds around it than the carbon would like to have. So as we get closer, as the attack occurs, it becomes higher and higher energy, all that repulsion from those electrons, till we reach the high energy transition state. And this is where our trigonal bipyramidal transition state, as the bromine bond breaks and the hydroxide bond forms, and then we fill in the rest of the molecule like we did, C2H5. That's going to be the high energy transition state that we have there. We've got all this electron density around that carbon, much more than it would like to have. It's very crowded. But then, as this bromine completely breaks, we'll start to lose energy as the bromine gets further and further away from it until the reaction comes to completion, and we end up with our products and our, what else are we going to have? Br minus, like that. So the reactants, our high energy transition state, trigonal bipyramidal, as the bond is breaking and the new bond is forming, and then we end up with our products as that loses that energy. Let's now compare that to our SN1 reaction that we said occurs in 2 steps. The first step involves the initial breaking of the old bond. So in this case, our halogen leaves and that initial bond is broken, and this gives a carbocation intermediate. So this is why this happens in the tertiary carbocations, because they're much more stable when compared to the primary carbocations. This is a slow step. So that means we call it SN1 because there's only one reactant involved in the slow step, in the rate determining step, and in our case that is the halogenoalkane. Because as soon as the carbocation is formed, the nucleophile will find that positive carbocation and immediately and very quickly form the new bond. We get attacked from the nucleophile to form the new bond with the carbocation. As the rate is only dependent on one species, that's where the number 1 comes from. Now this occurs in tertiary halogenoalkanes, like I said before. The relative stability of tertiary carbocations and a greater level of steric hindrance. So let's first consider the carbocations. We have much more electron donating groups attached to it. We have 3 alkyl groups as opposed to just the 1 alkyl groups. That means we can have a much more positive inductive effect to stabilize that carbocation. The other effect is steric hindrance. Well, we said that the steric hindrance isn't a factor because primary halogenoalkanes aren't congested. They don't have big bulky groups around them. But if we have a tertiary carbocation, which if I draw an example over here, if we got something like a chlorine, carbon, carbon, carbon like that. In this case, we have three very bulky groups all around, and the chlorine as well, all around that central carbon atom. So it's very congested. It's very much a lot more difficult for the nucleophile to get in and do it in one step due to the effect of all these big bulky groups around it. So unlike our primary halogenoalkanes, our tertiary halogenoalkanes have a large effect from steric hindrance. They're very congested. So these two factors combined means that they will occur in two steps. So let's look at this general mechanism. We said firstly that the bond is broken. We'll see the leaving group leave, and then we form the carbocation intermediate. That leads us to the second step. We have very quick attack from the nucleophile. That will give us our substitutive reaction. Now, something worth noting, it's not particularly pertinent to us at this point, but if we consider the stereochemistry of these kinds of mechanisms, we can see some interesting things that are occurring. If our SN2 reaction, what we can see here is that we started with one optical isomer, if we consider this as a carbon with 4 different groups, and what we end up with is we end up with the other optical isomer, the enantiomer of it, because as the nucleophile comes in, we invert the stereochemistry of that central carbon atom, and you can see these three R groups are now on the opposite side. With our SN1 reactions, because we have the leaving group leave first, our halogen leaves first, we can get either the retention, the same stereochemistry on that chiral carbon, or if it comes in from the other way, we can get the inversion of the stereochemistry on that carbon. So we can actually see both enantiomers, they're called, both mirror images, if we have a chiral center at this carbon. Like I say, just something worth noting, not super important for where we are at this point, but you might find it interesting. Let's do a task now. Illustrate the mechanism for this reaction, but let's do a specific example of 2-chloro, 2-methylpropane, and hydroxide. Justify why the reaction would occur via an SN1 mechanism. So use what we know about here. Don't worry about stereochemistry or anything like that. Let's see what the answer would be when I flip over here. So we've got 2-chloro, 2-methylpropane. So I've got 3 carbons. 1, 2, 3. 2-chloro, 2-methyl. So you can see that we've got our tertiary carbocation. So the first step is we have the halogen leave. This is a slow step, and we form the carbocation intermediate, which would have its trigonal planar geometry. So with our 3 alkyl groups, we're donating electron density. We got a more stable carbocation compared to the primary. Then we would have attack from our nucleophile. So we've got a good nucleophile, we've got a good electrophile. This step would happen very quickly. That would attack that, we would form the new bond, and we would end up with our substituted product. In this case, an alcohol, a tertiary alcohol like that. So we can see that unlike before we showed the transition state, this time we're showing an intermediate. So we're also going to consider what that would look like on an enthalpy profile diagram as well. Looks a bit similar, but a bit different. Because we have a 2-step reaction, we see the reaction occurring in 2 steps, like so. So you can see there's an initial step, then there's a bit of a lull, and then there is a formation of the second step, and then the formation of the products. So let's consider this here. At the beginning, we've got our reactants. Then as this bond breaks, that takes energy, 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 energy. So we get a high energy transition state as this bond is breaking. Then it leaves and we form the stable, or the more stable carbocation intermediate there. Then as we form the new bond, we get another transition state, and then eventually we will form the bond. Well, I should say as the nucleophile gets in closer, we get a high energy transition state, and then as we form the bond, we will get our product. Let me draw that over here. So we've got something that looks like this. We've got our reactants, we've got 1 step, carbocation intermediate, 2nd step, formation of the products. So in our example about 2-chloromethylpropane, our reactants are going to be, oh, my pen's running out, going to be here. So I got 2-chloro-methylpropane, and I've got the hydroxide. So what happens is that bond leaves, that breaks, that takes energy to break that bond. So we end up with a transition state here, which is as that bond is being severed, something like that. Transition state like that. So then that leaves, and then we get our intermediate here. We get our carbocation intermediate. So that would be this species here. I mean, I guess I can do that as trigonal planar, can't I? Because that is what the VSEPR would dictate. So we form the carbocation intermediate. Then as the nucleophile comes in with its lone pair of electrons, requires a bit of energy to overcome all the electron clouds around it. And then we would get another transition state as that new bond is being formed. And then the bond forms and we end up with our products over here, which would be the alcohol like that, and then the chloride having left. So you can see we've got our 2 steps, the breaking of the bond, the forming of the bond, and we have our carbocation intermediate in the middle there, reactants and our products. Hopefully that helps you to illustrate how these mechanisms occur. So just to summarize all of that, we have our SN2 reaction occurs in 1 step, where we have a high energy transition state, which is our trigonal bipyramidal as the bond is breaking and forming at the same time. Conversely, our SN1 reaction occurs in 2 steps. So the bond breaks, we have a high energy transition state, we form a carbocation intermediate, which is stable because of the 3 alkyl groups that are attached to it, positive inductive effect, stabilizing that positive charge. Another high energy intermediate as we make the new bond, and then the bond is made and we form our products like that. To finish today, I just want to touch on some other stuff which is important for our halogenoalkanes. Before I even do that, I mean, there is a whole class of halogenoalkanes that we've just completely ignored, isn't there? What about the secondary halogenoalkanes? And the answer is they tend to do both mechanisms. So it would depend a little bit on what the secondary halogenoalkane is. It would depend on the reaction conditions. It will depend on the the nucleophile that is involved. So whereas we can generalize and say that our primary do SN2 reactions, our tertiary do SN1 reactions, our secondaries tend to do both. Okay, let's talk a little bit before finishing today about reactivity and that carbon-halogen bond strength. Reactions are often heated to give reactants more energy, and this will increase the reaction rate. But if we have volatile organic compounds and we heat them up, they're going to go into the gaseous phase. And if they go into the gaseous phase and we've got no way to control that, they're just going to dissipate and we're going to lose all our reactants and all our products and we won't make a reaction. So something that chemists can employ is a technique called reflux, which is very common and very, very useful. It involves the use of a condenser that allows the reactants / products to constantly move between the gaseous and the liquid phase to both increase the chance of successful collisions and to give our molecules energy greater than the activation energy. So reflux looks like this. Lab technique that allows the continuous heating at high temps without the loss of volatile organic compounds. So in this condenser tube, we run cold water down the bottom, and then up the top, that's constantly being in cycle so that the water doesn't heat up, it remains nice and cool. So as we heat up the reactants and they go into the gaseous phase, we will have more successful collisions, more molecules with energy greater than activation energy, and therefore more products formed. However, we don't lose any of our product theoretically because it will condense, it'll cool back down here, back into the liquid phase, go back up into the gaseous phase, liquid phase, gaseous phase, and you can do that for however long you need to help the reaction occur and get more products, increase your yield. So if we consider the hydrolysis of halogenoalkane using silver nitrate, this is a reaction that is done under reflux. So we can also form the alcohol, not using aqueous alkali, but just using water. However, because water is a much less effective nucleophile than the hydroxide, we can do it under the reflux to help that reaction occur. This also ties into a little bit about when we're looking at using an aqueous versus an ethanolic solution. And if we use the ethanolic, it means we don't have water so that we don't get competing reactions to potentially form the alcohols, because the hydrolysis can occur just with the water. Okay, so we get a similar reaction here to aqueous alkali, but it's a slower reaction. Water is not as good of a nucleophile, but we still end up with the substituted chlorine for a hydroxy, which gives us an alcohol. Now the rate of hydrolysis will depend on how easy the carbon-halogen bond will break. The easier it'll break, the quicker it'll occur. The less easy it breaks, the longer it will occur. So let's consider the relative bond energies. And what we see is our carbon fluorine, very strong, and then we decrease the bond energy as we go down the group. And this makes sense if we think about how close the shared pair of electrons is to each of the nucleus. As we add a quantum level into our halogen, it's going to get further away from the nucleus that's holding it between the carbon and the halogen, and therefore the bond is going to be a bit weaker. So we can observe this and we can measure this by doing this hydrolysis in the silver nitrate, because we saw before how aqueous halides will give a precipitate when they form the silver salt. If we form the silver chloride, the silver fluoride, the silver iodide, etc., we form a colored precipitate, tying back to our qualitative analysis. So that will form if we've got silver nitrate in our hydrolysis under reflux here, because we're going to form the halide that can then form the salt with the silver. So if we do this reflux and we measure the time taken for each of the halogenoalkane, if we start with the chlorohalogenoalkane, then the iodide, then the fluorine, then the bromine, etc., and we see how long it takes to go opaque, so therefore how long it takes the precipitate to form, we can determine that the most and the least reactive halogenoalkanes, and we see this trend. The slowest nucleophilic substitution takes place with fluoroalkanes. That's because they have the strongest bond, so it's going to take more time to break that. The fastest with the iodoalkane because they have the weakest bond, and then everything in between there. So we can see reactivity, how that relates to our carbon-halogen bond strength. And with that last little bit, we have concluded our halogen derivative topic. What have we learned today? We've looked at the following nucleophilic substitution reactions of bromoethane, hydrolysis, formation of nitriles, formation of primary amines by reaction with ammonia. We looked at a lot of those in the previous lesson as well. Describe the SN1 and SN2 mechanisms of nucleophilic substitution in halogenoalkanes, including the inductive effects of alkyl groups. Recalled that primary halogenoalkanes tend to react via SN2 mechanisms, tertiary halogenoalkanes via SN1, and secondary halogenoalkanes via a mixture of the two, depending on their structure. And right at the end there, we touched on interpreting the different reactivities of halogenoalkanes with particular reference to hydrolysis and the relative strength of the C-halogen bond. Your tasks: pause, consolidate, and you will be golden. Excellent work. Getting through another unit. Very well done. I will see you as we start the next unit next time. Have a fabulous day. Good job.